Hello, everyone, and welcome to Lecture 30 of Computer Architecture. Today, we're going to talk about associative caches. Last time, we were talking about memory and cache, and the time before, we spoke about caches and how they're organized. And last time, we looked at how to have caches with large block sizes, so where every cache block is multiple words. And we saw that the advantages of caches with large block sizes is that we amortize the overhead of the tag bits, and we also are able to capture spatial locality, because when the block is large, if we're bringing in the word, we bring in all the words that are next to it. So if a program has spatial locality, it will find the nearby words already in the cache. But we said that the disadvantage, if we assume a fixed cache size, is that we have fewer blocks, which increases our miss rate. But also we underutilize the blocks if we do not have spatial locality. So if a program does not access nearby blocks at the same time, then we would have brought those blocks in for no reason. And because our blocks are larger, it takes a longer time to bring them in, so this means that our miss penalty is larger. So those are the advantages and disadvantages of increasing the block size. And last, we spoke about writing to caches, and we said that there are different cache designs based on how they deal with write hits and how they deal with write misses. So based on how they deal with write hits, say a cache could be a write-through cache or a write-back cache. A write-through cache will try to update the memory as well as the cache, whereas a write-back cache will only update the cache and will update the memory when the cache block or cache line gets evicted. And to know that it needs to update the memory, when it updates the cache, it'll set a bit called a dirty bit on. So we're going to have an additional bit in the cache called a dirty bit. And it sets this bit so that it knows that when the cache line gets evicted, to go and write it back to memory. And in both these cases, we said that we have a write buffer so that we don't have to wait for the write through or the write back to complete when we write or when we evict. We also said that based on how they deal with write misses, we have two different cache designs, a write allocate cache and write around cache. A write allocate cache, if we have a write miss, we'll fetch the block, put it in the cache, and then write to it. Whereas a write around cache, if we on a write miss, will not fetch the block, it'll just go and write directly to the lower level in the memory hierarchy. So that was a quick overview of what we covered last about this material. Okay, if there are no questions, then today we're going to optimization for caches, and that is associativity. So we're going to look at associative caches. So last time, and the time before, we considered a direct mapped cache. And a direct mapped cache, we had multiple blocks in the memory mapped to a single block in a direct mapped cache. And what that means, in this case, what that meant is that these two blocks always have to go in this one block. And because of that, I have a program that is kind of simultaneously needs to access both of these blocks. So if I have a program that needs to go to this block, and then this block, and then this block, and then this block, then this block, and this block. So if a program needs both of these blocks together frequently, what's going to happen is I'm going to keep bringing one into the cache, then I'm going to evict it to bring the other one, then I'm going to evict the first one to bring the second one, then evict the second one to bring in the first one, and I keep doing that. And what we call that is we call that thrashing. So when we're in a situation where we have blocks that conflict and we keep bringing them in and out of memory, we call this thrashing, and this really hurts our performance. So what we'd like to do is we would like to design a cache that helps us avoid, to the extent possible, this behavior of constantly bringing blocks in and out just because they conflict on the cache block. And to do that, what we're going to do is we're going to add associativity to our caches. Now, what does that mean? Well, an associative cache is a cache that's organized into sets. So rather than having 8 different blocks and each block has its own index, what we're going to do is we're going to have 4 sets of 2 blocks, and every set is going to have its own index. But a block with the index of a certain set can go in either block in the set. Okay, so rather than having a cache with 8 blocks, each with different indices, we're going to have a cache with 4 sets of 2 blocks, and each set has its own index, and it has 2 blocks that can have memory blocks that map to this index. Okay, and here these 2 blocks we call these ways. So here in this case we have 4 sets, and every set has 2 ways. Now what this means is, in our previous example, where we had these 2 blocks that were conflicting on the same cache block, now these 2 blocks, they have the same index, so they're going to map to the same set here, set 1, 0, because they both end with 1, 0. They're going to both map to the same set. However, this set has 2 ways. So what that means is I can put one of the blocks in one of the ways and the other block in the other way. And the advantage of this is that now, even though these 2 blocks conflict because they have the same index, they can still both sit inside of my cache, and I can still access them both without thrashing the cache. So this is in general the idea of this is kind of the idea of associative caches. Okay. Now, in general, we say that we have an n-way set associative cache when a cache has n, when each set in the cache has n blocks. Okay, so we say we have an n-way set associative cache when each set in the cache contains n blocks. Now, what does this mean for reading the cache? If each set in the cache has n blocks, this complicates reading the cache a little bit, because now if I want to read the cache and I go and I have a particular index and I look up the blocks at that index, I have multiple blocks. I don't just have one block. So what that means is I need to search all the entries in a particular set at once, and to check because any of them could be a hit, and also none of them could be the hit. Okay, so this is one thing to consider when we are designing an n-way set associative cache. And a special case of an n-way set associative cache is a fully associative cache. Actually, a direct map cache is a special case of an associative cache where we just have one set. And a fully associative cache is another special case of an n-way set associative cache, which is the other extreme, where the entire cache is one set. So a fully associative cache, a block can go anywhere in the cache. Okay, so you can think of the whole cache as one set. And just like with an n-way set associative cache, we had to search all the entries in the set that matches our index. In a fully associative cache, we're going to have to search all the entries in the cache at once to find our hit. Okay, so this is some information about or terminology about caches. We have the direct map cache we saw before, and now we introduce the set associative cache and the fully associative cache. Okay, any questions so far? Okay, well, having considered this, oh, someone's asking what is the relation between n and n. Excuse me here. So here n and n should both be the same. Okay, so this is a big N, this is a small N, this should also be a capital N. Excuse me for the mistake. Okay, so so the spectrum of associativity. So if I have a cache with 8 blocks, there are different ways I can organize this cache, right? I can organize it as a direct mapped cache, right? Or which is also another one-way set associative cache, where I have 8 sets and every set has 1 block. So this is direct map cache. I can organize it as a two-way set associative cache where I have 4 sets and every set has 2 ways or 2 blocks. Okay, and notice that each block is going to have its own tag, right? So the first way we're going to have a block and it has its own tag, and the second way also has a block and has a tag, because these 2 blocks are going to contain completely different memory blocks. So I need a tag for each of those memory blocks. Okay, a 4-way set associative cache, here we're going to organize the 8 blocks as 2 sets where each set has 4 blocks. And then we have an 8-way set associative cache, which in this case is the fully associative cache. The fully associative cache, I'm simply going to have one set with 8 blocks. And each one of these 8 blocks is going to have its own tag. So basically, if I want to look up something in this cache, I'm going to have to compare to all the tags. Okay, So we have a spectrum of associativity. There's a trade-off between the number of ways and the number of sets if we want to keep the size of our cache fixed. Okay. All right. Well, given kind of what we've said about caches, let's take a look at how we address a cache. So given, let's say we have a cache that has 256, which is 2 to the power 8 sets, and in each set we have 4 ways. Okay. Let's say we have a cache with 2 to the power 8 sets, and each set has 4 ways. Notice how each way has its data, its tag, and its valid bit. Okay. And let's say that each data, for simplicity, let's say that each data in the block, each block is just going to be 1 word, okay? That we're doing this for simplicity just so that we don't have to show how we select different blocks, okay? So in this cache design, if we have a 32-bit address, the question is, how do we take this 32-bit address and subdivide it in order to index our cache? Okay, how do we take a 32-bit address and subdivide it to index our cache? Well, first of all, each block in the cache is 1 word. So the lower 2 bits in my address are going to be the byte offset. Okay, the lower 2 words here, sorry, the lower 2 bits in my address are going to be the byte offset. So these lower 2 bits distinguish the different bytes inside of a single word. So these are not going to be useful for indexing my cache. Okay. So next we have the block offset, but here we said that every block is exactly 1 word. So we're not going to have a block offset. The block offset is going to be 0 bits. Okay. And next I have my index. So how big is my index going to be? Right, 8 bits. So I have 2 to the power 8 different sets in my cache. So my index is going to be 8 bits. So the next 8 bits I'm going to use to index the 250 sets in my cache. Okay, so I take these 8 bits and I use them to index the cache. Now what do I find? I find 4 different cache blocks because this is a 4-way set associative cache. So every set has 4 different blocks. So when I use these 8 bits to index my cache, I'm going to find 4 different blocks. Now the data that I'm looking for could be in any of these 4 sets, in any of these 4 ways, or it could be in none of them. So what do I need to do to find out if my data is in any of these sets and which one? Sorry, if my data is any of these ways and which one? What do I check? Right, exactly. So it's just like we did before. We need to check the valid bit and we need to check the tag. So here we're going to look at the valid bits for all the different ways in my cache. So we're going to check the valid bits for all the ways to check that if any of them are not empty. And we're also going to check the tag for all the ways in my cache. So here we have 2 bits for the byte offset and 8 bits for the index. So I have 22 bits remaining for the tag. So we're going to extract these 22 bits, and we're going to compare the tag in the address to the tag in all 4 of the ways. And we're going to do this in parallel. Okay? So we're going to read the valid bit and the tag from all 4 ways in the cache, and we're going to check them. Okay? And like we did before, the valid bit and the tag for each way is going to be passed. So here we're going to compare the tags to check if any of the ways match. Okay, and then the valid bit and the tag for each of the ways is going to be passed to an AND gate. So here for each way, if the valid bit is set and the tag in the way matches the tag in the address, then we know we have a hit in that way. Okay. So now we know we have a hit signal. Now, obviously, only one of them is going to hit or none of them, right? Because I'm not going to have the same cache block in 2 different ways. So either one or none of these different ways is going to hit. So how do I know if my cache hit? How do I know if my cache is a whole hit? So my cache is going to hit if one of these ways hits, correct? So how do I check? Right, exactly. I order them together. So I'm going to take these hit results for each of the ways, and I'm going to order them together. Okay, and if one of these AND gates gives me a hit, that means that my cache has a hit. And if none of them give me a hit, so if all of them are 0, so all the ways miss, that means my cache has missed. Okay? Right, now let's say I have a hit. What do I do when I have a hit? Okay, so someone is asking, if I have a miss, how do I check which one? Well, it doesn't really matter, right? Because if you have a miss, that means the set access to the set missed means that the add, because this address could be in any of these ways. It doesn't have to be in a specific way. Okay, so if you have a hit, you care about which one, right? If you have a miss, that means access to the set missed, not access to a specific way missed. Okay. But of course, if you have a miss, you're going to have to bring in the cache, the memory block into one of these ways, and we'll talk about how to do that later. How to select which way we're going to bring it into. Okay, but now if I have a hit, I need to return the data, right? How do I return the data? Where do I get it from? So the data could either be the data in this way, or the data in this way, or the data in this way, or the data in this way, right? So how do I select the right data and return it? What do I use to select? Come on, guys. We should know this by now. What hardware structure selects? Correct, a multiplexer. So what we're going to do is we're going to pass this data to a multiplexer. We're going to read these data from the cache, and we're going to pass them to a multiplexer. Okay, and the multiplexer is going to select one of them as the data. Which one does it select? How does a multiplexer know which one to select? It should select the one that hit, right? The multiplexer should select the data that corresponds to the way that has a hit. So I already have the hit signals over here. And guess what? They're already in one hot encoding, right? These hit signals are already in one hot encoding. So I can use the hit signals and pass them to the multiplexer and also use them to select the data that I want. And notice that here, my hit signals are already decoded. They're already in one hot encoding. So my multiplexer is going to be simpler. I don't need to have a decoder. Okay, because only one of these is one. So I pass these directly to each one to select one of these lines. Okay. So this is a summary of how a set associative cache works. This is a summary of how we use an address to access data inside of a set associative cache. So someone's asking, the multiplexer here is just AND gates. I mean, it could be AND gates or it could be a three-state buffers, right? But the point is that in either case, you don't need a decoder because your select signal is already decoded. Your select signal is already in one hot encoding. Okay. Any questions? Is this clear to everyone? Okay, so let's take a look in general about bits in an associative cache. And to make this interesting, I'm going to make this a write-back cache. Okay, so let's say we had an associative write-back cache. Okay, how are my bits going to be divided? So if I have a cache with 2 to the power n sets and 2 to the power m bytes per block and w weight, how do I divide my address when I'm accessing the cache? Well, first of all, my lower 2 bits are going to be the byte offset, so that's not going to change. Okay. What about my block offset? How big is my block offset going to be? Right, m minus 2. If I have 2 to the power m bytes per block, that means I have 2 to the power m minus 2 words per block. So my block offset is going to be m minus 2, exactly. What about my index? Right, my index is going to be n. And notice that the key difference here is that before I had 2 to the n blocks when it was a direct map cache. Now I have 2 to the n sets. So I don't care about how many blocks I have. I care about how many sets I have. So here, the index is going to be n, where I have 2 to the n sets. Okay? The number of blocks is going to be 2 to the n times w. The number of blocks is going to be 2 to the n times w. However, I don't care about the number of blocks. What I care about ultimately is the number of sets. Okay, so that's why we have an index of n. And what about my tag? What's my tag going to be? Assuming a 32-bit address, of course. Right, so my address is going to be, well, not exactly, 32 minus m minus n. So it's 32 minus the total of this. So n plus m minus 2 plus 2 is going to be, it's going to be n plus m. So the tag is going to be 32 minus m minus n. Okay? Let's look at the size of our associative write-back cache. Okay. We have, first of all, the number of blocks is going to be 2 to the n times w, right? We have 2 to the n sets times w ways. Okay. How many data bits do we have? So we have 2 to the n times w blocks, and every block has 2 to the m byte, right? And every byte is 8 bits. Yes, exactly. So the number of data bits, the number of data bits is 2 to the power n times w times 2 to the power m times 8. What about the number of valid bits? How many valid bits do I have? Right, so we have 2 to the n times w valid bits because we have 2 to the n times w blocks, and we're going to have a valid bit for every block. Okay, now this is a write-back cache. So what does it have besides a valid bit? Right, so each block is also going to have a dirty bit. So since this is a write-back cache of dirty bit, how many dirty bits do I need? Right, exactly. Also 2 to the n times w, because every block is going to have a valid bit and a dirty bit. What about our tag bits? How many tag bits do we have? So every block is going to have its own tag. So it's going to be 2 to the n times w times the size of a tag, which is 32 minus m minus n. And then the total size, and like I said, the total size of the cache is going to be this over here. So 2 to the n times w times 2. This 2 is 1 valid bit and 1 dirty bit, plus 32 minus m minus n, this is the size of the tag. Then 2 to the m times 8, this is the number of bytes per block. Okay? Any questions about this? And by the way, kind of here, before we did an example of a direct map cache that was not write back, and now we did an example of associative cache that is write back, but you should not confuse these two things, okay? So you could have a direct map cache that's a write back cache. You could have an associative cache that is not a write back cache, okay? So don't confuse these two things. But I'm just doing this because in our previous example, where we did this for a direct map cache, we had not introduced write back caches. All right, so having this, let's do an example of an associative cache. So let's say we have a two-way set associative cache that has 4 sets and 8 bytes, which means 2 words per block, okay? And let's say our memory is an 8-bit address memory, okay? So first of all, what does this cache look like? Well, it's going to look like this. We have 4 sets. Okay, so we have 1, 2, 3, 4 sets, and we need a 2-bit index to index 4 sets. Okay, it's a two-way set associative cache, so every set is going to have 2 ways. So every set is going to have 2 blocks. Okay, and then we have an 8 bytes per block. So we're going to have 2 words per block, word 0 and word 1 in each block. Okay, so given this cache over here, let's take a look at how let's go through a sequence of memory accesses and take a look at how they interact with our cache. Okay, so let's start with this one. So let's say we have this address over here, 10110000. Okay. Well, to look at how this address is going to be used to address this cache, we need to break it apart into the tag and the index and the block offset and of course the byte offset. Okay, so how do we break apart this address? How many bits is my byte offset going to be? No, my byte offset. Right, so the byte offset is always 2 bits, right? The byte offset is the one that selects the bytes within a word, and we don't care about that. That's always going to be 0, 0. So these 2 bits are going to be my byte offset. How many bits is my block offset going to be? So remember, the block offset is going to select the words within a block, right? So how many words do I have in my block? I have 2 words, so how many bits do I need to select? I need 1 bit, right? So basically, my block offset is going to be 1 bit. So in this case, it's going to be this bit over here, 0. Okay. What about my index? What's my index going to be? How many bits? Right? I have 4 sets, so obviously my index is going to be 2 bits. Okay, so here, in this case, it's going to be 1, 0. And how many bits is my tag going to be? 3 bits, exactly. So the remaining bit. So here, this address is going to be broken down into the 0, 0 byte offset, which we don't need. The next 0, which is the block offset. Then 1, 0, which is the index. And then the 1, 0, 1, which is our tag. Okay? Now, since our index is 1, 0, we know that we are supposed to map to this set over here. Now, this set has 2 different ways. Okay? So what we're going to do is we're going to check if either of these ways are valid and have the data that I want. So in this case, do either of my ways have the data that I want? Right, no, because because they're both invalid. So in this case, do I have a hit or a miss? Right, I'm going to have a miss. Okay, I'm going to have a miss. So since I have a miss, what am I going to do? I'm going to bring in the data. I'm going to put it in the first empty way. So here, I'm going to put it in this way over here. Okay, and what I'm going to set my valid bit to 1, right? And what I'm going to put my tag over here. Okay, so I set the valid bit to 1. I put my tag over here, 101, and then I read in the data from memory and I put it in my cache. And then what you notice here is that this cache has the block in the cache has more than one word. So in this case, we're only interested in word 0 in the cache line. Okay, and here we're going to use the block offset 0 to select word 0 in the cache line. However, we're going to bring in both words. And because we brought in both words, in the future, if I come to access the next word in the address, I will find it in my cache. So if my program has good spatial locality, if my program accesses both word 0 and then word 1, then I'm going to find word 1 in my cache, and then that's going to help me with spatial locality. Okay? So these are just a few things to take into consideration. So there's a lot of things going on. We index the cache, we figure out our valid bit, we set our tag, and then we kind of figure out which of the words is the one that that we want using the block offset. Okay, so the index selects the set, the tag determines whether the cache line is valid, and the block offset selects the word. Okay, let's now have another address. So now we have this other address over here. What is my index in this case? Right, my index is 0, 1. What is my tag? 1, 1, 1, correct. And what is my byte? What is my block offset? 1, exactly. So here my tag is 1, 1, 1, my index is 0, 1, my block offset is 1. So what we're going to do is we're going to use our index to find the set that we care about. So here the set is 0, 1. Is my data in the memory, in the cache? My data is not in the cache, correct. So since my data is not in the cache, I have a hit or a miss. I have a miss, exactly. So what I need to do is I need to bring in the data to the cache. So I'm going to bring in the data to the cache. I'm going to set the valid bit. I'm going to set the tag to the tag over here. So this tag is going to be 111. Okay. And I'm going to bring in both words to the cache. And then I'm going to use the block offset, which is 1 this time, to select the word that I want. In this case, it's word 1. Okay. Clear so far? Any questions? Okay, let's do a few more addresses. So the next address is this. Okay, what's my tag? 100. What's my index? 10. What's my block offset? 0. Okay, so what we're going to do is we're going to use the index to index the cache. Okay? So do I have a hit or a miss now? I have a miss, correct. Why do I have a miss? Right, because the tag is different. So in this case, my tag is 100, but the tag that I have in this way is 101. So I have a miss in the first way because my tag does not match, and I have a miss in the second way because the valid bit is 0. Okay, so I have a miss in my cache. Now, previously in the direct map cache, if I had a miss and I had something sitting in my cache block, I had to evict it in order to bring in the new memory block. But the nice thing now about the associative cache is that even though I have something in this way, I have another way that is empty. So what that means is that I can bring in the data at this address without having to evict the data that has the same index. Okay, because I have multiple ways. So what I'm going to do is I'm going to check, oh, well, this way is full, but this way over here is empty. So I can bring in the data at this address and put it inside of this way. So I will set the valid bit to 1 over here. I will set my tag to 100. I will bring in both words into my cache, and then I'm going to use the block offset to select which word that I want. In this case, it's word 0. Okay? So this is kind of a nice example of how having set associative caches helps me avoid evicting cache lines too frequently. Okay, let's do the next address. So the next address here, I have 101.101.100. Okay, what's my tag? Right, 101, and my index is 10, and my block offset is 1. Okay, so I'm going to use my index 10 to index my cache. Do I have a hit or a miss? Right, I have a hit. Why do I have a hit? Because my tag, which is 101, matches one of the tags in the ways, which this is this tag over here in way 0. Okay, so I have a hit. So since I have a hit, I'm going to use the block offset to select the word that I want. And in this case, it's this word over here. Okay, now there's multiple interesting things that just happened here. The first interesting thing that just happened is that first I have a hit. If I had a direct mapped cache, what would have happened is that this way over here, this cache block over here, may have evicted this cache block over here because they have conflicting indices. Okay, so I might have had a miss, but because I had a associative cache, I was able to kind of put the conflicting block in the other way and keep the block in the first way around so that in the future when I came to access it, I will find it. That's the first interesting thing that happened. The second interesting thing that happened here is you'll notice that when I previously accessed this cache line, right, when my index was 10 and my tag was 101, which is over here, the block that I accessed the word that I accessed was word 0. My block offset was word 0. So previously I accessed word 0. I actually have not accessed word 1 in this cache block before. Okay? Now, if the cache had only 1 word per block, then this would have been a miss. Right? But because my cache has 2 words per block, when word 0 came in from the first access, word 1 came in with it. So later on, when I came to access word 1, I found it. So here, is my hit benefiting from temporal locality or spatial locality? Spatial locality, right? Spatial locality. Because temporal locality is where I find something in my cache because I accessed it before, I'm going to access the same thing again. Spatial locality is where I access something in my cache and I find it because I brought it in when I brought in something that was close to it. So in this case, the reason I'm hitting is because of spatial locality. If my cache only had 1 word per block, then I would not have had a hit over here. I would have had a miss. Okay? And if my cache only had 1 way, then also I would not have had a hit over here. I would have had a miss. So here this hit is benefiting from spatial locality, and it's also benefiting from associativity. Okay, so let's do one more example. So here I have 11010000. So what's my tag? 110. Okay, what's my index? 10. What's my offset? What's my block offset? 0, exactly. So here I have 110 is my tag, 10 is my index, 0 is my block offset. So I'm going to use my index 10, and I'm going to come here and I'm going to index this. I'm going to find this set. Do I have a hit or a miss? I have a miss. So what do I need to do because I have a miss? So before, when I had a miss, one of the ways was empty, so I just brought in the data into the way that was empty. But now I have a miss, and both ways are full. So what do I need to do now? Right, I need to evict one of them. I need to evict one of them. So before, with a direct mapped cache, when I had a conflict like this, when I had conflict on the index, when the block at the particular index was full, there was only one block for me to evict. I didn't have a choice. I evicted the block that was there. Now with a set associative cache, now that I have a conflict, and what the blocks at a particular index are full, if I need to do an eviction, now I'm faced with a choice that I need to make. Which of these blocks do I evict? Do I evict the first one or do I evict the second? So what do you guys think? Which block should we evict? We can evict either, right? It would be correct either way. But in terms of kind of what would be the better one to evict in terms of performance? Right, the oldest used. So the point is that we need some kind of replacement policy. So a replacement policy is a policy that helps us select which block to evict when we have no empty blocks available. Okay. Now with the direct map cache, like I said, we only have one choice. There's only one block at each index, so there's no choice. But with a set associative cache, right, now we have a choice because we have multiple blocks at each index. And here there are different approaches that are used depending on the set associative cache. So the one popular one is least recently used. Okay, so the cache block that we haven't used in the longest amount of time, we're going to evict that one. So this is the least recently used policy. We're going to choose the one that's unused for a long amount of time. Now, least recently used requires us to check, to keep track of which of the cache blocks was recently used, right? And this is actually a difficult thing to do if you have many ways. So it's simple if we have a two-way set associative cache. It's manageable for up to 4 ways. But beyond that, it becomes very hard. If we have many ways, it becomes very hard to keep track of which cache block was recently used. So for low associativity, least recently used is feasible. But once the associativity gets high, the least recently used becomes infeasible because we have many different blocks to keep track of which one was recently used between them. Okay, but it turns out that actually for a very high associativity, random works just fine, because with very high associativity, you have many blocks. So if you randomly select one of them, it actually gives a similar performance to a least recently used. Okay, so in order to use a least recently used policy, so if I was going to use a least recently used policy over here to evict one of my cache blocks, which block should I evict? The one in way 0 or the one in way 1? Right, way 1. I should evict the one in way 1. Because if you remember, first, when we access the index, if we look at all the places where we access index 1, 0, right, first we access the tag 101, which is this one. Then we access the tag 100, which is this one. And then we came back and accessed the tag 101, which is this one. So the one we most recently used was the 101. So the one we least recently used was the 100. So even though this 100 came in after 101, we actually used 101 the most recently. Because we used 101 after we used 100. So in this case, according to the least recently used policy, we should evict the cache line in way 1. Okay, so like I said before, we have a miss. And because we have a miss, and both cache lines are full, we need to evict one. We're going to evict this one, and we're going to remove it, and we're going to replace it with the tag 110. We're going to bring in the data, and then we're going to use our block offset to select the data that we want, which in this case is the data in word 0. Okay? Is this clear to everyone? Any questions?
Memory. When we have next, we have 8 possible tags, right?
You're breaking up, so I can't really tell what you're asking. Could you try to say it again, or maybe type it in the chat? So someone else had a question in the chat. Does word 0 and word 1 have the same value? No, word 0 and word 1 do not have the same value. Okay, they could have completely different values. Here I just have an X to indicate that we have data, we have valid data here, but they don't have to be the same value. X here doesn't indicate a value, it just indicates the existence of a value. Okay. Someone's asking, for each index there are 8 possible tags. No, for each index we have 2 blocks, and because we have 2 blocks, wait, you mean for each index there are 8 possible tags, as in, yes, because so the tag is 3 bits. So for each index there are 8 possible memory blocks that can map to this index. What do you mean by having 8 possible tags? So someone's asking, if we want to have 8 ways, we can only have 1 set. Well, I mean, it depends on what you want to do. If you want to keep your cache size fixed, then if you want to have 8 ways, you should have 1 set. And so in this case, it would be a fully associative cache. Okay. All right. So a final comment. Yes, go ahead.
Why don't we take into consideration the one which we use the most? Why is it the most recent one?
So there's actually different ways of having a replacement policy. One way is doing least recently used. Another way is doing least frequently used. Okay, so least frequently used is also a possible policy that you can have. But if you think about it, just because I use something frequently, it does not necessarily mean that this is the one that I want to use again in the future, right? Because if basically every value that I'm loading I'm using 8 times, then if I've used something 8 times and you've used something else 5 times, right? It's most likely the case that the one I've used 8 times I no longer need, whereas the one I've used 5 times I still need. So if I use the least frequently used policy, I'll evict the one that I used 5 times instead of the one that I used 8 times, even though I might still need the one that I used 5 times, and I might have used that more recently than the one that I used 8 times. Okay, so least frequently used actually favors the data that's been in the cache for a longer time, but that's against what I would like to do. I'd like to the data that's been in the cache for a longer time is probably data that I will no longer need, whereas the data that I just brought into the cache is probably data that I will need in the future. And that is why a least recently used tends to be a better policy than a least frequently used policy. Okay. All right, so a final comment. The question is how much associativity? So we've seen that associativity can improve performance because it reduces the evictions because when we have conflicting indices. Okay, and what that means is that it would reduce our miss rate because I'm no longer going to miss because something that was in my cache got evicted because of a conflict. But where do I stop? How much associativity do I have? So the advantage of increasing associativity, like I said, it's reducing the miss rate because I reduce the cache lines that are evicted because of conflicts. But this has diminishing returns. And if we do a simulation, this simulation of a 64 kilobyte data cache, it shows that as you increase associativity, you reach a point where you don't get as much benefit improvement from increasing associativity. On the other hand, the disadvantage of increasing associativity is that it increases hit time. Why? Because when we have multiple ways, we need to check all the ways, and then we have this multiplexer that's selecting data between all the different ways. And this additional multiplexer and these additional checks take more time. So increasing associativity increases our hit time, but it decreases our miss rate. Okay, and the other disadvantage of increasing associativity is that we need more hardware because we need all these additional comparators for the tag, and we also need this multiplexer, etc. So there's advantages and disadvantages of increasing associativity. And next time we're going to look a little bit more systematically at the trade-offs that go into cache design and the trade-offs that come with associativity and all the other optimizations that we talked about with regarding caches. Okay. More about what we covered today, you can refer to section 5.4 in the textbook. And next time we'll talk more systematically about about the different factors that impact cache performance. All right, that's all for today, and I'll see you next time. Bye, everyone.